All right, so we have our person running at a rate of 2 meters per second. We want to fill in the table to find their distance for 0 through 5 seconds. So if 0 seconds have passed, how far have they gone?
0.
They haven't gone anywhere. Yeah, 0. What about after 1 second? 2, then 4, 6, 8, 10. So is there a constant difference if we look at our table? Yeah, what's our constant difference?
Every 2 seconds, or every 1 second, you go 2 meters.
Yeah, every 1 second we go 2 meters. So we've got a change of 1 second for our time and a change of 2 meters for our distance. So we've got that constant difference. We go 2 meters per every 1 second. That's constant for us. That's constant for us. So it's easy for us to find. We could easily find if they've been running for 10 seconds how far they've gone because that change is constant. It's 2 meters every second they go. Now, my challenge to you is, and this is stuff that you guys would have done last trimester, that constant rate of change. See if you can write an equation to represent the situation. Let's have time be x and our distance be y. So take a minute, see if you can write an equation that can represent our situation, or looking at our table of values too. See if you can write an equation. So if we go to write our equation, we can rely on our science classes if we want. You guys have probably heard, or maybe not even this year, maybe in years past, distance equals rate times time. Well, our distance we're representing with y. Distance we're representing with y. What's our rate? How fast are we going? 2 meters per second. So we've got 2 for our rate. And then our time, what variable are we using for time in this situation? We're using x. So there's our equation. What I want you to do, and again, this is similar to something you would have graphed last trimester. Take a minute and see if you can graph that equation. What form is that equation in? We've got the y by itself. Y equals mx plus b, right? Little slope-intercept form. See if you can graph it. See what you remember. Again, this is last trimester stuff. Let's see what we remember. All right, so if we have y equals mx plus b, that means we've got a slope. Our m is married to the x, so our slope is a 2. I like my slope to be a fraction, so I change it to 2 over 1, 2 meters per 1 second. And then my b, we don't have anything added or subtracted, so what could we put for our b? A 0. Yeah. So we start at our y-intercept, which is 0. My slope is 2 over 1. Rise over run. Up 2, right 1. Up 2, right 1. Now, instead of going up and right, how else can we move? Ooh, Jonah.
You could look at the your graph there, where you have all the numbers, you can graph it that way.
Yep, you could graph from your table also. And then the other way we can move for our slope could be down 2 and left 1. So just to get us a nice idea of what our graph looks like. Now, for a given situation, are those negative values applicable? Can we have negative time? No. Can we have negative distance? No, we can't. So if we were to name the equation we wrote, what do we call an equation whose graph makes a straight line? Linear. Yeah, linear. It even has the name line in it. So all last trimester, for the most part, when you guys graphed, kind of depends which teacher you had. Some of you graphed absolute values, some of you did not. The main type of equation you guys all graphed last trimester was linear. Slope-intercept form was one of the ways you graphed that. So that is what we're used to graphing. We're used to graphing those straight lines. Today we're going to move on and see what happens when we start involving some exponents. So here's something for you to think about. See if you can fill in the table. Every person has two biological parents. Again, I want to stress that we're looking at it from the biological standpoint, not adoptive, step parents, none of that, just biological. Everybody has two biological parents and 4 biological grandparents. Finish the table below to show how many great-grandparents we would have. Great-great and great-great-great. See if you can find that pattern. See if you can find that pattern. What do you think? Just fill in the table and let's go from there. See what you think. All right, so our number of great-grandparents, each grandparent had 2 parents each, so our great-grandparents is going to be at 8. Great-great-grandparents, what's our pattern we're showing here? What are we going to have?
16.
And then we're going to have?
32.
32.
Is this like a real life situation? How do you have 16 great parents?
Great-great-grandparents, because each of your great-grandparents has 2 parents each. So each one of so you have 2 parents. Again, we're talking biological. I know some of you have step parents, adoptive parents, foster parents. Just talking biological. You have 2. Then each of your parents had 2 biological parents. So we get 4 grandparents. Then each grandparent had 2 biological parents. So we jump to 8. Now each great-grandparent has 2 biological parents. So we jump to 16. So each one of those people has 2 biological parents. So for each one person, we've got 2 parents for them. So now in our first example, we said there was a constant difference. Our time kept going up by 1, and our distance kept going up by 2. As we look at our table for our parent situation, do we have that same constant difference? No, we don't. So take a minute and think about it. So no constant difference, so no. What's the pattern you see? Take a second, write it down. What's the pattern? How do we get from you to your parents to the grandparents to the great-grandparents? What's the pattern that we see? Yep, we're multiplying everything by 2. So multiply. We're multiplying by 2. For the linear stuff, what you guys are really used to from last trimester, for the linear stuff, we kept adding the same number each time. So we had a constant difference. With the linear stuff, you're adding or subtracting the same number each time. Now as we're moving forward, now we're seeing that pattern not being an add or subtract, but now we're seeing it being a multiply in this case. So now when it comes to the equation, I want you guys to play around with this for a little bit. You're going to use all the same pieces as your linear one. You're going to have a y equals, you're going to have a 2, you're going to have an x. See, though, if you can write an equation, though, that represents our pattern of multiplying by 2. You're going to have a y equals, I'll tell you that much. And on that right side, you're going to have a 2 and an x. But what do you have to do with them so our pattern is multiplying by 2 and not the add subtract like we saw up above? Just take a second and play around with that. I want to see what we can come up with. Now, I saw a lot of people as I walked around were just doing this. Is that the same as what we wrote in part 1?
Yes.
Yeah, we just have a dot there for multiply instead of writing the x right next to the 2. So if I do 2 times x, that gives me a difference of plus 2. That gives me that straight line. I don't have a plus 2, I have a times 2. So think about the work we've been doing. In order to get 2, then times another 2, then times another 2, we need exponents in there. So 2 to the power of x. Now you might be thinking, whoa, wait, Miss Kelly, I'm not buying that. Let's check it out. Let x be X is our number in parentheses. That's how many generations came before you. If I have 2 to the 0, what do I get? I get 1. What if I have 2 to the first? What do I get? 2. 2 to the second is 4. 2 to the third is 8. So if your pattern is multiplying, we're not going to do 2 times x. We're going to do 2 to the power of x is what we're going for. Now we want to get an idea. When we had that linear equation, our graph was a nice straight line. If my pattern is now multiplying by 2, we're not going to get that same straight line as when we were just adding 2. So part D says use your equation from part C to find the values when x is -1, -2, -3. So I need to see what this graph does when it moves into that negative piece. I know negative doesn't make sense when we're trying to figure out grandparents and things, but I want to see what this graph looks like. So if we put -1, 2 to the negative first, where do I move that so the 1 becomes positive? Where does it go? It goes down below. So we get a 1 over 2. So we get a half. 2 to the negative second, where does it move to? Down. And 2 to the second is just 4. And then we have 2 to the negative third. Again, we move that down. And we get an 8th. So we get some little numbers there. So we're just moving our negative exponents to the bottom. Negative exponents from the top down to the bottom. Now you might be thinking, Miss Golly, how do we graph those? Well, let's start graphing the part that we know how to graph. And we're just going to graph what fits. So we're going to have our first ordered pair. We're going to start with the U box, and that's 0, 1. Then we're going to go to the parent box, and that's 1, 2. The grandparent box is 2, and then 1, 2, 3, 4. The great-grandparent box is 3, and then 8. The great-great-grandparents, we're getting up to 16, we're not going to fit. We have enough points on there, we don't need to change our scale to make all those fit. But now you might be wondering, okay, Miss Guys, when x is -1, my y is a half. How do I graph that? I'm not used to graphing fractions. So all that means is, we're going to go -1 on the x, and then just do your best to go up half of a box. Then the -2, 1/4. Go to -2 on the x, and then these get tougher as you go. Do your best to go up 1/4 of a box. When you start graphing small fractions, a lot of times the points look the same because the boxes are only so big. And then we have -3 and then 1/8. Yep, we're getting really close there. So when I had positive exponents from our table up above, all my results were positive values. When I had negative exponents, all my y values were once again positive. There's nothing I can put in for that exponent. We just spent a lot of time with those exponent properties. There's nothing I can put in for my exponent that's going to make my output or that y value negative. This graph isn't going to go negative. So when we draw this in, it's a nice curve. It's going to get close to the x-axis, which represents 0. And then it's just going to keep increasing up. So it's not going to drop down negative. I can't get anything. I mean, we've got 2 to the 0, 2 to the first, 2 to the negative first. I can't get a 0, and I can't get anything negative. So this equation, we name it, this is an exponential. Because our x is an exponent. So if your x is an exponent, you've got an exponential equation. The graph is that curved shape that we see that we just created. Okay, so this first part that we did, I just wanted to show you. Part 1 is what you're used to. That constant change of 2, that straight line graph, that's what we're used to. Now we're moving forward with, well, what happens if I'm not adding or subtracting? What if I'm multiplying to get my next values? That's going to result in an exponential equation, and that's what a basic exponential graph would look like. Okay. Now, what I want to do, that was just to introduce them to us, go to the back side of the first sheet. And I want us to pick apart just some of the basics of the graph. Not worrying about any kind of application with it, grandparents, running, nothing like that. Let's just look at the basics. Now, if you have a graphing calculator, go ahead and take that out. In your graphing calculator, we're going to graph. That first equation says y equals 2 to the x. So we're going to go ahead to the y equals. It's highlighted red on my screen. Top left corner. I know we did this one of the days last week, but we just only graphed one equation. So the y equals top left corner. Anything I press or ask you to press highlights red on my screen. So if you don't find it on yours, take a look up at mine and see if you can locate that on yours. If not, let me know. Now we need 2 to the x. So we're going to type in 2. And then we need to do an exponent. So we do the little up arrow, that little caret key. Now mine might look different than yours. It depends on what type of calculator you have. Some of you might just get the little arrow right on your screen, and that's okay. The x key. I know we talked about it last week, but we only did one equation, so we might not remember. The x key we need is the one next to your alpha key. It has an X, a capital T, a little sigma, and an N on it. And that's all we need for right now. That's all we need for right now. Now, in order for us to make sure we can see a nice graph, we want to adjust what's called our window. We're going to go to our window. And we always want to start with, -10 for the x minimum. Remember, that's how far left we see on our graph on that x-axis. 10 for our x max. X scale of 1. Our y minimum, that's how low we see, how far down our y-axis goes. I'm going to go -10 on that. And +10 for the y max. It's just a nice starting point. Now, with some of our exponentials, we might end up with some really big numbers, and we might have to change that window, and that's okay. We'll cross that bridge when we come to it. We want to make sure we start with our nice viewing window. So we're going to go ahead, and we're going to press graph. So there's the graph that actually we drew on the front side of our sheet with our parent-grandparent example. Notice how our graph gets really, really close. I know it looks like it crosses the x-axis, but not quite. Now you might be thinking, okay, great, Miss Golly, so the calculator shows me what the graph looks like, but how do I get that on my paper? You want me to make a table of values. Here's the cool part. Press your second key. Mine's blue. On some of the older calculators, it's yellow. Press your second key. Then press your graph key again. Up above the graph key is the word table. Super cool, right? Up above your graph key is the word table. You might have to... Oh, and mine just froze. Whoa. Yikes, mine just froze. Sorry, guys, let me try that again. There we go. And if I scroll, I can get everything I need. So again, I pressed my second key, mine's blue, yours might be yellow depending upon the model calculator you have. And then I press the graph key. Now you might have to scroll a little bit. Look at my x values. I have -5, -4, -3, -2, -1, 0, 1, 2. If you're on a different part of your table, just scroll. So your values might not be matching mine right now because you might be in a different part of your table. You have to just kind of scroll around a little bit on your table. So all I want you to do on your note sheet is go ahead on that table piece and go ahead and write down the values that you need. Now, that middle column, Miss Golly, what happens if I don't have the graphing calculator? I forget how to do it. To get those y values, guys, all the calculator is doing is putting each x value into the equation. So 2 to the -3rd on your calculator, it's going to tell you it's 0.125. And that's okay. I'm okay with that because that's getting so small. We're not going to be able to exactly graph those, whether we write them as a fraction or a decimal. Doesn't matter. And then we have 2 to the -2nd. Well, that's just a 4th. 2 to the -1st comes out to be a half. 2 to the 0 is 1. 2 to the 1st is 2. 2 to the 2nd is 4. 2 to the 3rd is 8. So if you need to get a graph of an exponential, guys, we have these awesome tools. We have these calculators. Now, if you borrowed one of mine, you can only use it during class because I need it for my other classes. But we have these awesome tools. Let's use them. Let's make this graphing thing a little easier for us. So the calculator will show you on the screen, hey, here's what your graph should look like. And then it gives you a table of values to help you graph it. So let's go ahead and graph those. It might be easier to graph like the 0, 1 first or the 1, 2.
Is that how you know the middle row is like what's on the x side? Is that how you get the exponent?
Yep, the exponent is what the x values were. Yep.
Okay.
Yep, the x values are just what we put in for our exponent. Absolutely. And then let's see, 1, 2, 3, 4, 5, 6, 7, and there's 8. And then our little decimal ones, guys, we're going to just do our best. We have a half, a fourth, an eighth. We're going to just do our best to sketch those. Make sure you have an arrow on both ends. As you guys looked at that table, the list of values, it keeps going and going and going. So on this graph, though, you can scroll all you want on that table. We're not going to get a y value of 0. We're not. We're going to keep getting closer to it. Those y values will keep getting smaller the more negative you go. We're going to get really close to 0, but we're not going to reach it. And no matter how hard we try, we can't get a negative for our y, no matter how hard we try. We can't. So what we like to draw in, I always like to draw in, it's just a little imaginary line. There's my barrier. There's where my graph isn't going to cross. It's going to help me graph it. We're going to talk about how to find that pretty easily as we get some different equations. Now, one piece, and again, it depends on which teacher you had last trimester, one piece you may or may not have talked about is the domain and the range of a graph. The domain of a graph, simply put, it's all possible x values. Or you might also hear the word input, because it might not always be x. You might write an equation that exponent might be a t. It might be an r. So all possible x values, aka inputs. What do we put into our equation? If you look at our x values, aka our inputs, could we put positive values in? Is that okay? Yeah. Could we use 0 for our x? Yeah, we did. Did we have some negative x values too? Yeah. The possibilities for x are unlimited. I can put any value I want for an exponent. I know we haven't done it yet, but I could put a fraction for an exponent. You guys will get to that in Algebra 2. But we could. So my list of possibilities for my x values, I can put whatever I want in. If I can put whatever I want in for x, my inputs are unlimited. We say we have all real numbers can go in for x. If you want to abbreviate that, guys, you can put the symbol for the set of all real numbers, which is just, it looks like a kind of a double-legged R. And that's going to be the case for any of the exponentials that we do in this course. We're not going to do anything too crazy. We can have negative exponents, we can have zero exponents, we can have positive exponents. And again, we don't get there, but we can have fraction exponents. We just don't get there yet. So if the domain is all possible x values, what do you think the range is? All possible what? Y values, yeah, all possible y values. AKA, again, it might not always be y that you have. It's whatever that output variable is. So maybe you have a p equals, maybe you have a t equals. It might not always be a y. It's our output. Now, with the y value, with the exponentials, here's where we have to be careful. I can't get any output that I want. Our graph will never touch 0. Our graph is never going to drop below my red dotted line, and that's where all the negatives are. So my possible outputs for this, they're all living in that positive world up here. My graph is not going to cross down into the negatives. We saw it. No matter how hard we try, we have all positive y's. So in order to say we have all positives, this one's going to be all of our y values are greater than 0. If you want to make a little note there, that means they're all positive. You sure can. The domain for our graphs, the possible values we can put in for x, that's not going to change. It's not going to change for any of the ones that we do. The piece that will change, though, will be our range. We will be moving this graph around a little bit, and then our range will change, but we'll talk about how we can figure out that change. Okay? So this is a basic exponential graph. We had 2 as our base number. Let's see what happens. Let's finish up today seeing what happens when we have a fraction for our base. Let's see what happens. You might think, oh, Miss Golly, not the fraction piece. We're going to use the technology again, guys. But just so you're aware what the calculator is doing to get those y values, this would be 1/2 to the -3rd. This would be 1/2 to the -2nd. We're just replacing the x in the equation with the x that's listed. Oops. Oh, now it erases. So if you're wondering, well, wait, Miss Guy, the calculator's just giving me this magic table. Where does it come from? We're just putting x values, aka our inputs, into our equation for x. So when the calculator gives us a value of 0, 1, that's why. I put a 0 in for my exponent. So the calculator is doing that work for you, which is totally cool. We're going to get to how we do the fractions. So let's jump to the calculator. Let's get this as easy as possible, right? Go to our y equals. And I'm just going to go ahead and clear out what's there in our y1. Let's go to our y equals. Now, if you have a TI-83 plus, so look at the top of your calculator in the upper right-hand corner above your screen. If you have a TI-83 plus, here's how you enter your fractions. You're going to put a parenthesis, 1 divided by 2, close your parenthesis, then do your exponent. So do your caret key, that's that little up arrow looking thing, and then our exponent is an x. So if you have a TI 83 plus, you can actually do the same thing on the 84s as well. It's okay. TI 83 plus, you don't have a choice. That's how you have to enter. That's just how it's programmed to do fractions. Now, if you are a TI 84 plus user, you have the option to enter a fraction. So you're going to do alpha. You're going to press the alpha key and then y equals. You're going to get a separate menu that pops up. Alpha y equals. And you want option 1. And then you'll get the fraction. And we'll do 1. Just use your arrow keys. And then we have the exponent x. So if we graph, we have same shape, opposite direction. Go second graph, get your table of values. Go ahead, fill them in on your sheet, and go ahead and sketch your graph. All right, so we have 8, 4, 2, 1, a half, a fourth, and an eighth. So notice even on your tables, guys, our tables are going opposite too. Our tables are opposite as well. And again, we see that we don't have any 0 or negative exponents. So my imaginary border there that we're not going to cross is still at that 0 line. So I can still put anything I want in for x, so all real numbers. My y values, I still can't get 0 or negative, so they're still just going to be all positive. So today we looked at 2 basic exponential equations. What's the basic shape? A little bit on domain and range. We'll pick this up tomorrow.